So the next talk is about distinguishing attack on NORX permutation by Tao Huang and Anjun Wu, and Tao will give the talk.
Okay, thank you very much for the introduction. So today I'm going to talk about the distinguishing attack on NORX permutation. This is a joint work with Anjun Wu. So here's the outline of this talk. First, I will give an introduction. Then I will talk about the distinguishing attack on NORX 64 permutation. Then the distinguishing attack on NORX 32 permutation conclusion. So NORX is an authenticated encryption algorithm. It's designed by Encryption, Java, and Native. So it's now one of the 15th around data candidates. It's very efficient in both software and hardware, so that's a very nice design. The current version is NORX version 3.0. It has 5 instances, so they differ in the word size and the round number and also the branch number. Here's an overview of the NORX AE scheme. So it takes the nonce and the AD message, then it will output a tag. The NORX state is divided into a 4x4 matrix, like shown here. So the first row are the read part, and the last row is competitive. The state size is either 1024 bits or 512 bits, depends on the word size. Now let's look at the NORX permutation. So the permutation is denoted by FL, where L is around is either 4 or 6. Here we just consider the 4 round case, and then the F is a round function. It has 2 parts. The first part is a column step, and the next part is a diagonal step. So here is the picture. In the column step, it applies the G function to each column. So there are 4 words in each column. And then it applies G function to each of the diagonal. So it's like the cha-cha. Then the G function. This function has the following operations. Half of them are nonlinear operation, and another half is a linear operation. So the nonlinear operation is H function, which is like the simulation of modular addition, but is using XOR, and the shift. Here I talk about the notation on the quarter round. So it's naturally one round NORX is separate to 2 half round, either the column and the diagonal. And for each round, if we further separate them to half, so the first 4 operations and then another 4 operations, then we have a quarter round that we will use in the later analysis. Here are the security bounds for NORX. So we know that it's based on the so-called multi-duplex mode. So this mode is supported by security proof. The security level is minimum of the 2 to half of the block size, due to the complexity and due to the key size, showing that the underlying permutation is an ideal permutation. So whether this permutation is ideal or not will determine whether the security proof works or not. So we look at some cryptanalysis on NORX permutation. First is by Arson et al. They analyze the differential property of NORX permutation when the difference is only introduced in the nonce parts. So the results for the 4 round permutation is very low probability for both versions. And that's et al. analyze the high-order difference property of the non-equal permutation. They give some distinguisher for 4-round NOX 64 and 3.5 round for NOX 32 permutation. But their distinguisher requires chosen intermediate state. So basically, they need to choose the value of intermediate state and then propagate the state backward and forward. So it's not something starts from the beginning. Then Chernow et al. Proposed an attack on the full primitive NOX 32 in last year's FSE. So this is a very interesting attack. It uses the structural property of the NOX run function, that it is actually rotational identical for each column. This structural property works no matter how many runs of the permutation. And we have another analysis by Gilcroft et al. So it's using a symmetric truncated differential, which can result 2.125 round distinguisher for both versions. First summary of our results. Now we propose a new distinguisher attack on 4-round NOX permutation with low complexity. So for NOX 64 permutation, the time complexity is 2 to 48.5. And for NOX 32, the time complexity is 2 to 64.7, and the memory complexities are negligible. Now we go to the details of the distinguishing attack. First, NOX 64 permutation. We give a recall on the differential linear attack. So it's proposed by Nahor and Hellman in a couple of years ago. The idea is to first divide the cipher into two parts, the differential part and the linear part. Then the introduce difference in at the beginning and the analysis statistic of the XOR sum of the output linear mask field. We will start by constructing linear characteristic. First, we try to give linear approximation of the G function. This is done by remove the nonlinear function, nonlinear operation n. So it's something look like this. And we'll try to express each bit of the inputs in terms of the bits in the outputs linearly. So eventually we find that the bias of input bits depends on the word, it's A, B, C, or D, and also depends on the position of the bits. So when the position is 0, when the position is 1, and when the position is greater than 1. So it's interesting to see that sometimes it has unbiased bits, which means that those bits we cannot use in the analysis. So with this linear approximation, we can search for the linear characteristic. We consider the input linear mask to have one active bit, and we find that the position 0 has best bias. So this reduces the search space. What we find is a 1.25 round linear hash. When C0 is active, it has a very good bias, which is 2 to -8. Here we look at an example of the linear characteristic. The only active bit is here in the inputs, and there are a number of active bits in the output mask. Then we come to the differential part. So there are 2.75 round differential characteristic. We divide it into 3 phases. Phase 1 has 1.75 rounds, and both phase 2 and 3 they have a half round. Notice that we derive it in reverse order, so that the actual difference first comes into phase 3 and then propagates to phase 1. For phase 1, we let the input difference be 1 bit arbitrary input difference, and output difference be the difference on specific bits, which is input linear mask. Then we experimentally search all the 1 bit difference, and the best one we found is this bit is 10.7. So after this round, it has bias minus 2 to minus 3.9. Then the phase 2, we propagate this 1 bit difference backward. So we use a linear approximation of H function so that we can get this input difference in phase 2. Of course, we need to pay some price for this linear approximation. It has probability 2 to minus 5. Then in phase 3, similar to phase 2, we again propagate the difference backward. But here we have probability 1 in this phase because we are able to derive initial conditions. Here are some examples of the initial conditions. So suppose that we have this linear approximation of H function by A1 equals H A0 B0. Then we only need to set a condition such that B0 equals 36 equals 0. Then this linear approximation holds with probability 1. A more complicated example is here. When we have the nonlinear function on C and C0 and D1, then we need to control a number of bits to make sure that the linear approximation holds. Then we repeat this for every linear approximation. Then we will get many conditions on the bits. And we need to make sure that this condition they do not have any contradiction. So we give the whole picture of the differential linear characteristic. Here is the input difference, and this is the output linear mask. This is the estimated bias. It's minus 2 to minus 22.9. Now we are able to present the distinguished attack. The attack procedure is to first query 2 to 47.5 pairs of messages, and for each pair of outputs, we compute the actual sum of the bias in the gamma out, which is the output linear mask. Then count the number x such that the output of the actual sum of the output is 0. Then we compare this value to a critical value. If this value is smaller than the critical value, then we conclude that this oracle is NORX permutation. Otherwise, we think it's random permutation. The complexity is 2 to 48.5 time and negligible for memory. The probability of success is 96%. We have experimentally verified this result. So we use a GPU server with 4 Tesla K40 GPUs. Then we generate this number of pairs and then compute the statistic. It takes 3 hours. And what we find is the bias in output bits is minus 2 to minus 88, which is very close to the estimated one. Now we come to the distinguishing attack on NORX32 permutation. Basically, it's quite similar to the NORX64, so we will omit the details and we give the result here. So we have this differential linear characteristic and this differential linear bias, which is -2 to -31.2. This is initial conditions. And the complexity of this attack is 2 to 64.7, and the probability of success is at 6%. Now I conclude this talk. So we found the 4-round NORX permutation. They are not ideal because they can be distinguished with relatively low complexity. And this distinguishing attacks on the permutation does not directly lead to attacks on the real authenticated encryption algorithm, because in the real case, the input cannot be injected to arbitrary places, and also the output bits are not fully known. And I want to remark that the complexity of the attacks may be further improved by controlling the initial difference for more rounds. So that's all for the attack. Thank you very much for your attention. Any questions?
Still no questions? So I just have a short question. When you mentioned the complexity of the attacks, the complexity is higher for the smaller version, right?
Yes.
Could you explain why it's this way? Or
oh yeah, because in the large version, actually the active bits are more sparse. Yeah, because the state size is larger. Yeah, so when you consider the conditions, it's actually better for the attacker. Yeah.
Okay, the differential part.
Yeah.
Thank you. Next one, the speaker again.